All right, so welcome everybody to this weekly seminar. It's actually not really weekly, but I think most everybody follow the Bachelier and the SIAM seminar regularly. So it's a great pleasure for me to introduce Damir. You know, this is the standard sentence we use when we introduce someone, but you know, if you read the announcement and if you read this bio, you have to be impressed. And except instead of going through the bio, I would like to say a few personal anecdote about Damir. So I first met Damir together with Jean-Pierre Fouque and Rama Kont in one of the earliest conference in Ascona. And I was, you know, after dinner, we had conversation about infinite dimensional fixed income model. And I was impressed by this tall, articulate young man. And when a few months later, I had the opportunity to read his PhD thesis, I was impressed. A little bit shocked also because he did in a very clean and neat way what I was trying to do with Mike Taranci. But as a result, I was thrilled when he accepted to come to Princeton for his first real job. Unfortunately, he didn't stay with us too long, just a short year and a half, but I had the opportunity to learn a lot from him, and in particular, the theory of affine processes he was developing with the very famous people, Duffy and Walter. So he, you know, he left Princeton to go back to Europe to work for the federal government in Switzerland, and then academic position in Austria, München, before going back to Switzerland, where he's now holding not one, but two chairs, one at the EPFL and one with the Swiss Finance Institute. So, you know, I am going to give him the floor, but before that, I have to admit that Damir, like many people, got the virus, not the coronavirus, but the machine learning virus. But I think that for him, that may be a little bit a return to his first loves. And I suspect that today we're going to hear about reproducing kernel Hilbert space, maybe. So Damir, it's with great pleasure that I give you the floor.
Thank you, Rene. That's very kind introduction. So indeed, this is about machine learning. This is about a joint project with Lucio Fernandez Arjona, who is with the Zurich Insurance Group, and myself. This is about portfolio pricing and risk management, and we aim at high dimensional problems. So we are using machine learning methods. It is a very applied, paper. You find the preprint also on SSRN and on Archive. And in this paper, we develop a computational framework for quantitative portfolio risk management based on the dynamic value process of that portfolio. We approximate and learn that value process from a finite sample. This is simulation-based, using polynomial features and shallow neural networks. We scale the dimension via feature learning that allows to reduce dimensionality. And we give a numerical implementation of some real-world insurance example, which comes from my co-author, who is with an insurance group. So what do we find? We find that the choice of our feature maps are good, they are tractable, they yield closed-form conditional expectations. That's what we need to compute. That makes the approach computationally efficient. The feature learning, which is data-driven, substantially allows to scale dimension. We will benchmark, compare the three the three examples that we will implement, where of the shallow ReLU, rectified linear unit neural network, outperforms the polynomial features, even though not significantly. We also see that regress later outperforms regress now. I will speak a bit about that in what follows. So as I said, this is a rather applied paper. I have just recently developed some more theoretical insights, and I will actually tell you a bit more in this talk. So I first formalize and introduce the problem, and then we speak about the ways we approximate the payoff function of the portfolio that we will study, and then I will go more systematically into these three examples of feature maps. As you can see, these are polynomials with and without dimensionality reduction, and then these shallow neural network. And then at the end, I give you some numerical results based on this from this insurance liability model example. So this is about an economic scenario generator. Is about marking to model. It's about model-based quantitative risk management. So we have to simulate the economy, and most economic scenario generators that you will use ever are of this form. You have some finite time horizon that you fix. Then you have some stochastic driver, which is throughout is going to be called X, which is having independent components time-wise. So we can think of X as being a discrete time Brownian motion, but it's very important that I make that clear from the beginning that this is not necessarily the case. This can also be a Levy type stochastic driver. The thing that is important is that these XTs are independent. They may even be depending on time, but they have to be stochastically independent. Then, as usual, if not otherwise stated, all financial values and cash flows that we see, they are discounted by some numeraire to take into account the time value of money. And then we have a measure that we call Q, which is the corresponding risk neutral measure. And since it's about risk management, we shall also mention the physical measure, even though in the examples that we will study, we will just make an assumption that they are the same. What is the objective? We consider a portfolio whose present value has to be derived from its cumulative cash flow by this time horizon capital T. So here it is. We write that as a function of the stochastic driver. And so it's a sum of the time T cash flows. Examples are including simple options, European style options, but then of course insurance liabilities and other asset-backed instruments, or derivatives books in banks. And the goal of this exercise is we want to find the value process of the portfolio, and the value process is just given to us by computing conditional expectations dynamically in time of the terminal cumulative cash flow, and we use this shorthand notation here, and filtration be generated by the stochastic driver. And this can, of course, be decomposed into what has accumulated by a certain time little t, which is the risk horizon that shall be of interest to us, and then the spot value of whatever remains. So as I said, we have this terminal time horizon. This is our valuation horizon. We look at the portfolio that generates cash flows throughout the time. And this capital T can be very large. This can be 40 years and beyond. And the little t is small. It's much smaller compared to big T, and that is our risk horizon. So what are we interested in? We wanna in the end we wanna model, or we wanna quantify the risk that that comes with a portfolio value changes over that risk horizon, which includes possibly cash flows by the little t. What are the applications then? The risk measurement. So we would want to measure that risk. So we look at let's say a 1-year P&L, and then we would like to compute some risk measure, value at risk or expected shortfall. Another application could be hedging, because once we have the value process as a dynamic stochastic process, we could of course then just follow that target by some, let's say, variance minimizing strategy, and so on. So this is, as been said, quite a universal framework, because essentially every economic scenario generator in discrete time can be brought in this form. And here's just a textbook example, the European call option. There is not much to say here, but just one thing to think about, this we would have stochastic interest rates. We could have stochastic, here we take a Black-Scholes model for a stock price. Everything is driven by some Brownian motion in discrete time, and so the payoff is a function of the trajectories of this Brownian motion, obviously. Okay, and then the maturity dates that we will look at in this project are 5 years or 40 years, and the goal would then be to compute the expected shortfall of the 1-year time, of the 1-year risk horizon, profit and loss. So we need to compute these conditional expectations of that function f, and that is a computational problem because of lack of analytic solutions in general. Right? F is somehow an algorithm, or is somewhat hardwired into your economic scenario generator, into your whatever system you're using. You can query F as much as you like, even though that might be time consuming, but you will not have an analytic solution for these conditional expectations. And then, as we all know, the brute force approach to do this via nested Monte Carlo is just leading to exponentially large sample and sizes, because we have to nest outer simulations with inner simulations. If we just want to do it for one fixed time risk horizon, that may be fine, but if we want to do it for several at a time, then obviously this just exponentially grows. We also face a limited computing budget in realistic contexts. In the industry, we train on small data sets, so we are not simulating more than up to 50,000 trajectories of the stochastic driver in the end. And that, of course, then itself, leads again to possible overfitting, because we are training with small data sets. And we shall see, of course, what the effects are there. Now, there are broadly speaking, two approaches to do other than nested Monte Carlo. One is the regress now, and the other is the regress later. Let me speak now first about the regress now approach. This is, we fix a risk horizon, little t, and then we directly learn that value Vt, which is a conditional expectation, and therefore it's just an orthogonal projection in L2, and that, of course, is related to ordinary least square when we do this in sample. And so so this goes back to at least Longstaff and Schwartz in finance, who are using this approach for pricing American options. So they would choose some fixed basis functions, which are functions on the trajectory of x only up to the risk horizon little t, and then they would just regress the terminal value on these functions And then of course there has been huge literature in meanwhile, and so I just mentioned some of the latest papers here, which is by Brian Hughes and Antoine Savin. They also just presented it at EPFL a week ago, where they actually choose as basis functions, they choose a neural network. But we will do regress later, which is the following. We go and look at the terminal payoff or the accumulated cash flow, and we learn that by choosing a parametric feature map. So that means some functions, some basis functions, which are depending on some parameter, finitely many of them. And we assume that these feature maps have closed form conditional expectations. And when I say closed form, then this is not in a strict sense, but it could also mean that it can just be very, very efficiently computed. So that if that is the case, then obviously once we have approximated the terminal payoff in this form, then we can just compute the dynamic value process for all risk horizons then very efficiently by just computing the conditional expectations of these feature maps. Now, what is the error, or how could we control the error? And that's a very basic slide. That's just a very basic insight here, but it's nevertheless very useful because it combines two things. It combines that we have a martingale that we are estimating, and second that we are in fact learning the terminal value of that one, right? And once we have that bound, which by the way we can always estimate by Monte Carlo, then this gives us obviously immediately an upper bound on the relevant error. And the relevant error is again on a risk horizon. We want to know how far away are we in L1 with respect to the measure that we will base our risk measures on. And the risk measures that we will look at, expected shortfall, we know that they are well controlled by the L1 norm again. So if we are close here in L1, then our figures should also be our proxy figures should also be close to the ground truth figures that are of interest to us. Okay, so then let's now speak about this approximation. Let's very very generally give the frame here. And we have a parameter set. We fix some feature space dimension, and then we look at functions phi1 up to phi m that are depending on the parameter. We put them into this vector here that gives us the feature map. It's an Rm valued map, and of course we assume everything is in L2. And then we obtain the proxy of f by the L2 projection of f, which we denote here by f theta, and that's of course the solution to this least square problem for a given theta, for a given parameter. But now comes on top is that we will actually also learn that parameter from the data, meaning from the simulations of f, and that leads to some non-convex optimization problem, which is written up here. Okay, and it's clear if there is a solution to this problem, then the beta is of course given in terms of the optimal parameter theta, right? Okay, and then of course it's very elementary inside also to see that of course we can always express these loss, this L2 approximation error. We can of course also express it directly in terms of the feature map only without the beta involved, and so minimizing these loss function is of course equivalent to maximizing this function, which again is non-convex or non-concave, and so but we can so we wonder now, what can we say about the existence of that of this optimization problem, and so here is an elementary result, and which says that assume these three conditions hold, that the parameter set is a compact set, and that the map that maps the parameter onto the phi's is continuous, and that for every parameter we actually have a linearly independent set of functions. And under these three assumptions, then there exists a solution, and that immediately follows from what we saw on the previous slide, because then this function here is continuous, and so it attains a maximum. It attains the maximum on the compact set. Now, these conditions, this is a very elementary result, of course, but actually, these conditions are you cannot really get rid, right? You cannot improve. Having a general statement like that, you cannot further improve that lemma. And so that there are examples, and I don't go into the details here, but there are three examples which show that if compactness doesn't hold, or if this feature map is not continuous, or if we do not have linear independence for all parameters, then for all these examples, the infimum here is not attained. Okay, that's also why I write an infimum and not a minimum. Okay, now let's make that a bit more concrete, and so let's look at our working examples here, and all of these three examples actually have in common the following structure, right? So we are well, this is how we define the phi's. Okay, so we fix some functions gi, which are on some rp. By the way, the same, this d times t, is the d is the dimension of x, right? So d is the dimension of xt, and then we have capital T times steps. So the sample space dimension is d times t. Okay. And so what we will look at, parameters which are matrices and vectors pairs, and jointly with such functions gi, this gives us our feature map. Okay, and then of course as we are going to compute conditional expectations, we have a certain notational convention. We write this matrix here, A, or the transpose of it, and in this block form, and then of course that gives us the nice way of also writing here this A transpose X as a sum of the AT transposes XTs, and that is going to be useful, of course, whenever we then speak about conditional expectations, and that's what we look at now. So the conditional expectation of that is well, it's given here. It boils down to as we all know, of course, because the assumption was that the XS's are stochastically independent, and then of course computing such conditional expectation boils down to computing unconditional expectations, which we call here G theta IT, for whatever we observe so far. Okay, so and then that is the standing assumption that these unconditional expectations that can be computed very efficiently, right? Closed form for any mu here, which is an element in RP, and that is a placeholder for, of course, for the risk driver simulated up to the risk horizon. Okay, so in other words, that's how it will work then. Suppose we have this function, that can be very efficiently computed, and then we can, of course, very efficiently simulate let's say, the time little t value of the portfolio by just simulating again the stochastic driver up to little t, and then just query the function g. Okay, that's the idea. Okay, now let's look at these three examples. We start with the full polynomial basis, and then we see that this immediately leads to an explosion of dimension, and then we apply some linear dimensionality reduction, and then I will also look at some shallow neural network. So full polynomial basis. So here we just omit the parameters. So we just we just take the full basis of polynomials of degree delta or less on the entire sample path space. And so, I mean, then there is nothing to optimize over theta. So the existence we trivially have, uniqueness we have. The problem here, of course, is dimensionality. And so the example that we have in mind is driven by 5 Brownian motions. If we want to work with them with polynomials of degree 3 or less on a time horizon of 40 years, then we will have a dimension of 1.3 million. And remember that the sample size was of the order 50,000 or less. So, and that is obviously an hopeless overfit here. And so that we have to remedy. But before, just one slide on the conditional expectations, even though that should be obvious to you, that we can, of course, take an orthogonal basis here. And here I just show it for the Gaussian measures. Just take an orthogonal basis and take the tensor product or the product of the corresponding lower dimensional orthogonal polynomials, and then, of course, the conditional expectations are given in closed form. Good. Now let's deal with this dimension issue, and so let's look at the dimensionality reduction. So now we choose a p which is smaller than dt, and choose a basis of polynomials just in Rp, again of degree delta or less, but p will be much smaller than dt, and so this is then again our feature map, which is of this form. It turns out, and that's very convenient, a priori. We have any matrix in dt times p matrix, but it actually turns out that we can always assume that there is no bias, so the b is 0, and that A is actually an orthogonal, frame. So it's in this Stiefel manifold. It's an orthogonal matrix, and that is asserted to us by this theorem, which relates the spans of these polynomial feature maps, and it is clear that if we start with any A which has full rank, and then we look at A tilde, then this guy here is of course in this Stiefel manifold. So we can always restrict and have our parameter set the Stiefel manifold, and that's of course a nice compact manifold, Riemannian manifold. So it's nice to optimize over that one. And then what about the continuity? Well, under some integrability, under some moment condition, this is of course continuous, and linear independence is also can be shown to hold. Right? So the existence lemma applies, and so we know that there exists a global minimizer for the polynomial feature map under dimensionality reduction. That's good. That's the good news. And of course, it has a tremendous effect on dimensionality, as we can see here. So it's again about having a 5-dimensional random driver. We deal with polynomials of degree 3 or less, but we now kind of reduce the dimension of the dt here on down to 10, and then the space of polynomials itself has dimension 286. Of course, what we have to take into account is now the dimensionality of the optimization problem. Of course, now also needs to take account of the dimension of the Stiefel manifold, which however is moderate, as you can see here. So overall, we end up with a dimension in the order of 2000 and something, which has to be held against 1 million and something. Huh? So what about conditional expectations? I don't go into details here. The story is, again, we have pretty efficient ways of computing these conditional expectations. Of course, even though these polynomials on RP, we cannot nicely factorize anymore into the xt's, because the xt's now, the trajectories of the Brownian motions or the stochastic drivers, of course, they are now mixed also in time. But there's a beautiful paper here by Khan who presents this elementary formula which relates multivariate moments to sums of univariate moments. H here is a linear vector which is given explicitly, and so we only need to be able to compute the moments of linear forms applied to our random stochastic driver, and that is, of course, especially when it's a normal one, then again Brownian motion, then this is in closed form. Now the downside is we have non-uniqueness of the polynomial feature map, unfortunately. So there is not a unique, even though we have existence, but it's not unique. So the theta is not unique, and there are counter examples which can be constructed under the assumption that the function that we want to learn has the symmetry property for some orthogonal map on RDT, and also the measure, the distribution of X has to be invariant under this push forward. In this case, unfortunately, that we will have non-uniqueness of the span of this feature map, and so that's a fact we have to live with. All right, now about the shallow neural network. That is also something that you're, of course, all familiar with. We look at the rectified linear unit activation function. That's the hockey stick. And so the parameter a priori is matrix A and the vector B. The feature maps here are just these affine transformations of X and then the hockey stick of it. Now this is positively homogeneous for every I, so without loss of generality, we can of course assume that the vector AI BI is normalized, so that in the end we can assume that the parameter set is indeed a compact. It's just the n-fold product of the unit spheres. And so, towards the existence. So the question is, do we now have existence of an optimal ReLU neural network? Well, that is satisfied. Compactness, of course, continuity again here is satisfied of that map. So it remains linear independence, and then there you start to struggle, right? You start to struggle, and are these functions linearly independent? And my guess was in the beginning, yes, whenever the AI BIs are mutually different, then this gives us linearly independent functions. Again, see, here we assume AI BI are normalized, so they are on the unit sphere, but actually it turns out this is not enough. So, but what you need is that they are pairwise linearly independent, and then we have linear independence of the set of the files. And there is a counter example which shows indeed you cannot relax to pairwise inequality. That's not enough. So here is the example, and so existence lemma does not apply. We do not have existence. I mean that the existence lemma does not apply. Okay, but that was a general lemma. Now the question is, does that mean that for the ReLU neural networks we have non-existence, right? And then again, you start to struggle, and then you see, and then you find a counter example where you have non-existence. Okay, so the global minimizers do not exist for the ReLU neural network, and that's kind of, to me at least, it was well, I don't know, maybe some of you are, maybe this is a very obvious thing, or this has been well known. I had to find it out myself, and so So now, so then, somehow what we did with the polynomials, there's some alternative that suggests itself. We could define what we call a regular neural network when we then just restrict the parameters also to the orthonormal frames, to this Stiefel manifold, right? So not only are now the AI BIs normalized, but they also orthogonal to each other. And then of course, then we have no issue, right? Then we have no issue because, as we saw in this theorem that I quoted, then we have linear independence. And then, of course, the existence lemma applies, right? So we have existence under this assumption, but this is strictly restrictive, right? And you can show this is strictly restrictive, and I have a lemma 2 pages down. So that's good, but the non-uniqueness still remains, right? Even also for these neural networks, we don't have uniqueness in general. The counterexample goes similar as for the polynomial feature, even though here we can even be more, we can be very relaxed about what V has to be. This transform doesn't have to be orthogonal; it can be any linear transform, and as long as the measure Q is invariant under the push forward, and then again, we will arrive at 2 different solutions, which are giving us 2 different spans in general, as asserted by this following lemma here. But I do not go here into details. Now, the upside, of course, with these shallow neural networks, the ReLU shallow neural networks, is that when it comes to conditional expectations, then again, this is given very efficient. It's essentially closed form for many distributions, and in particular for the multivariate norm. Okay. Now, what do we do then in practice? So we have this optimization problem. Now we saw that for some models we have existence at least. We never have uniqueness apparently in general, but for the neural network even we don't have existence. But we just then solve it nevertheless using some gradient search that will find some good local minimum. And then, if the error is feasible, then if the loss is feasible, then we work with it. Okay, so we are using something from the literature here to optimize here. Each time we have a Riemann manifold. Well, for the polynomial case, for the neural network, we just use the scikit-learn built-in algorithms, and this finds us the local minima. And this is, what do you want? That's machine learning, right? And anyway, global minimizer would be likely to overfit. So, and so in the end, that's a bit the applied side of that project. And, we just implement it and see what is the result, because we can control the error, right? I mean, we can, of course, just look up what is this error and then decide whether we accept it or not. So then, of course, everything here I did under the population measure. Now, in reality, we would then sample, and so we would have to work with the empirical measure, and then we would just look at empirical versions of that optimization problem. Now, the theoretical issues still remain open, right? So we have this non-uniqueness, and sometimes even the non-existence of that optimal phi theta here. And then, so how could we ever get anything like consistency? I don't know. So this is an open issue, and I have not worked on it yet, and not anything about the guarantees. Okay, so now the remaining couple of minutes, I will tell you a bit about this insurance liability model example. This is a variable annuity with guarantee. So the story is the following: you have so the insured will invest a premium every year. So every insured pays a premium at the beginning of every year. this premium is invested in an investment fund, and that investment fund has some target allocation. It will consist of several assets, and then along with that we have a guarantee, and that guarantee grows with the premium. It's actually, the guarantee is actually the paid-in premium in this example. And then the following happens. So if so it's a life insurance contract. So if the person, the insured, dies within a given year, then the beneficiaries, they will get they will get the investment, the share of the investment fund, or the guarantee if the guarantee is larger. Everything is discounted here by the cash account. So here then these are nominal values. So here we have the cash account, and then these policies have a term, and so at the end you will just receive again your share in the account. If you survive, then you will also receive the share in the account or the guarantee if it's larger. So, and then we have 4 assets in this investment account. We have a 10-year, 20-year bonds rolling over, so they have constant maturity. We have an equity index and a real estate index, and we have a target asset allocation. And then, of course, we keep that target asset allocation whenever we receive a premium, and we invest it accordingly into the IF asset. Okay. And so here is the guarantee. This grows is just the premium that you pay that is guaranteed. And then there is a demographic model. So we have a mortality model. Right, that's the actuarial component. So we have the total number of deaths, we have the total number of surviving and policyholders who are alive, and the mortality is modeled with some death rate, which itself can change over time stochastically following the Lee-Carter model. Okay. So the stochastic model then overall is driven by 5 Brownian motions in discrete time. We have a short rate model where we use the exact discretization of the Hurwitz model, so that will consume 2 Brownian motions. And then we have a Black-Scholes model for equity and for real estate each. And we have the Lee-Carter mortality model. Each of them will consume 1 Brownian motion, but they will be correlated. Actually, these are correlated. That can easily be built in. X here is the standard Brownian motion. Then what are the objectives of that exercise? Again, we estimate the value process, right? And having done that, we then compute the present value. And we compute the 99% expected shortfall of the 1-year loss. We compare it to the ground truth, which we obtain by some large-scale nested Monte Carlo simulation. And we repeat everything so that we can also say something about the sample error distribution. So what are the quality metrics? We look at the mean absolute percentage error of the present value and of the expected shortfall. So here are the results. Actually, first an overview again of the 3 models that we will actually then implement. So the full polynomial basis on the path space. Here, these numbers we have already seen. Here we have this 1.3 million. This is not feasible. We cannot do regress later here. With the linear dimensionality reduction, where we go down to 10-dimensional polynomials, or polynomials in dimension 10. This is the number of parameters for the time horizon 40 years and 5 years. And the shallow neural network, here we have 100 hidden nodes. And we add one outer bias. And the number of parameters, therefore, is given by these figures here. So we see that also for the shallow neural network, we then still end up with 20,000 parameters. So this is the dimension of the optimization problem for the time horizon of 40 years. And now we can see the results. Some of the results. I will just focus on a few of these columns. So we have our three methods here: full polynomial basis, linear dimensionality reduction, polynomial, and the neural network. We also compare to nested Monte Carlo using the same sample size each time with an optimal split. So we give it the optimal split that we just basically, we do a hindsight benchmarking, the optimal split into inner and outer. So the sample size that varies from 1,000 to 50,000 trajectories. And these are the time horizons for the valuation, 5-year and 40-year. So this is void here because regress later for the full polynomial basis is not applicable to this large number of basis functions. But we also do regress now with the polynomials and with the neural network, and so as you can see, regress later outperforms. There's one exception here, but this is due to the small sample size compared to the, we still have over 1,000 basis functions here for the full polynomial basis case. Okay, but overall the numbers are fine. This is in percentage points, so we are in the order of 10 basis points or less with a relative error. And so here is the mean absolute percentage error of the expected shortfall, and this is a tough benchmark because it's a 99% expected shortfall of the 1-year loss. So maybe starting with the neural network, we see that here we have a relatively large error, which is due to the fact that we still overfit for this sample size, because remember that has 20,000 basis functions. But and you can see, there's a significant drop in this error here when we go to 50,000. So that's very nice. That's as predicted. Overall, again, we see regress later does better than regress now. And this one, it's remarkable. It performs remarkably well, and this is the polynomial with a dimensionality reduction. It for sure performs better than the full polynomial basis. Oh, excuse me, wrong. Sorry. So the full polynomial basis works with regress later only up to 5 years, in which case it does indeed better than this dimensionality reduction. That's not a surprise, of course. But then this only under linear dimensionality reduction we can go with the polynomials to the long time horizon here. Okay. All right. So here is the distribution of these errors that we just saw. And what about run times? And this is also an important aspect, of course. So we see that the neural networks, they run up to 2 minutes. This is on a single core. And the linear dimensionality reduction, that takes most of the time because we have to optimize over the Stiefel manifold that can take up to 25 minutes. But this is still feasible for that kind of model dimension. So that brings me to the conclusion and the summary of what I just discussed with you here. So I showed you a computational data-driven framework for quantitative portfolio risk management. Data-driven because we learn the features by looking at the simulations of the accumulated cash flow function. And we see that we obtain accurate estimates of the dynamic value process for relatively small training sample sizes. The feature learning in particular then also allows in the polynomial case to reduce dimensionality, which allows to then again solve high dimensional problems like this insurance liability example, where we saw that regress later outperforms regress now, and the neural network performs best, even though the polynomial feature under linear dimensionality reduction does quite well as well. All right, thank you.
Thank you, Damir. I think Rene will lead that.
All right, thank you so much, Damir. That was a very enlightening talk. So we have already questions on the chat. Petra, if you want to unmute yourself and ask the question, and if you can't, I will read your question to Damir.
Okay. Hello, thank you very much. Very interesting talk. I wanted to ask essentially how your approach connects to the Markowitz theory and how you manage to skip or overcome the correlation structure of your portfolio.
I'm sorry, I have to apologize. I had a bit problems to follow acoustically. Could you just repeat?
Okay,
Yes.
it's better now?
Yeah, it's better, yes.
Okay, I just wanted to ask how your approach connects to the Markowitz theory, namely, how can you overcome the correlation structure of your portfolio? How you deal with this issue, namely the correlations of the portfolio you are looking at?
Well, when you say Markowitz, I'm not sure if are you referring to some optimization that you want to also look. Is it about optimizing a portfolio as well?
Yes, yes.
Yes, but then in this case we are not optimizing. We take the portfolio and the portfolio allocation rules as given. We are for a given portfolio, along with their allocation rule and along with the strategy that has been basically scripted and coded. We are just simulating the cash flows, and then we compute conditional expectations of that. So there is no optimization step.
Okay, and in that case, what can you say about the risk?
The risk we are then modeling. We can quantify the risk by measuring expected shortfall of the P&Ls of that portfolio, and we can do it. We can do the unconditional expected shortfall for the 1-year P&L, but we can also do conditional risk measures, because we can really now then very efficiently simulate the entire the value process.
Yes, but this simulation then depends on the distribution that you are supposing.
Yes.
I mean, I wanted just to know how, since you still manage to calculate the risk, I'm impressed how the correlation structure of your portfolio does not come as the as one very, very important issue here. This fascinates me.
Okay. Okay, thank you.
So I don't mean to be rude, Petra, but you can continue this conversation privately if you want.
Yes,
So,
yes, thank you very much.
We are short of time. So if I do not see any other question, I have 2 questions for you, Damir. The first one is, if you are interested, for example, in computing Greeks or sensitivity of your outcome with respect to a certain number of parameters, do you have an issue with the fact that you're working with the ReLU function, which is not necessarily differentiable, or even the fact that you're working in L2? Do you need to work into a different type of Hilbert space, like Sobolev spaces, if you want to approximate derivatives or things like this? And my second question is related to, I'm rushing my 2 questions because I have to jump out at 2 p.m. exactly. You talking about overfitting, and like a classical statistician for which overfitting is a sin, is something that you want to stay away from. Well, apparently in the machine learning community, overfitting is something desirable, and there are a certain number of empirical evidences that overfitting is good. So how do you reconcile this new trend and what you said about overfitting?
Yes. Okay. Good. Thanks for the question. So I answered the first. The sensitivities and the deltas. That's a good question, and we have been thinking about it. I think what would be nice to do is to apply what people call differential machine learning, and that's also what the paper of Savin that I mentioned and the huge are doing, where you then not only learn about the function of the payoff value, but of the portfolio, but also you actually, not only these as labels, but also you look at the derivatives of these, and with respect to whatever you like, to parameters. And of course, this type of parameter dependency we would encode by just putting it into the stochastic driver, right? So let's say you just add something you call x naught, and then you stuck in all the parameters you like there, and then you give it a certain distribution, and then we simulate from there. So and then you can actually differentiate formally, and that can be done. And then of course the feature maps that we are using, you're right, it's a ReLU function there, but it still is almost everywhere differentiable, and that's what you do. So that should work well, but we haven't done it yet. But this is something we are on. Okay, I hope that.
Thank you. That's a good answer.
Yeah, which by the way, it would also lead to nice Sobolev space in a certain sense, right? Because we will then also look at L2 of the derivatives. Now, for the other question about overfitting, I understand that in machine learning, the overfitting has the advantage that you actually can find I mean, that is a way to deal with this local minimum problem, right? Because of this 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 is what you call the landscape, right? I mean, basically the loss function as a function of the parameter, the landscape, which is of course all but convex, and then it turns out that when you have overfitting, that your gradient search or whatever algorithms, your quasi-Newton algorithms are just converging better. Now, in our case, we just saw that overfitting is punishing you immediately, right? I mean, you saw it because the generalization just doesn't work. And we saw it in this table that I showed with the neural network, where we had, as long as we had more parameters than we had samples, we were just having a bad result out of sample, and then as soon as we don't overfit anymore, then it's much better. Now, why is that an issue? I mean, the issue here is that we are working with simulated data. We can simulate as much test data as you like, and that's actually the test data in our case is the simulated data that we then use to compute the expected shortfall, right? Which are then millions of samples, right? So there you immediately see when you have overfitting in the first place, because this generalization won't work. When you work with real data, you typically don't have such large test data sets, and then it's probably less visible, I guess.
All right, thank you. So I'm going to leave it to Agostino, who has an announcement to make. Thank you, Damir.
Thank you.
Thank you, Damir, for a great talk, and also Rene for moderating it. I would like to make some closing announcement. First, there will be no seminar due to Thanksgiving in the next 2 Thursdays from now. So we will resume directly with the early career talks on December 10. And as usual, information about past and future talks are available from the SIAG FME website. So please watch, take a close look at the website to watch the videos of past talks and see what is coming up. Second, I would like to say that the seminar is alternating with Bachelier. So next week it will be on Thursday a talk at the Bachelier Society. And finally, I would like to remind you to keep submitting mini symposium proposals for the SIAM FME conference. So the deadline is early December, December 3. So you still have some time. Please think about topics that you would like to organize mini symposium and contact the speakers and then submit. We are really looking forward to receiving all the proposals and to a great conference. And with this, I would like to end the formal part of the talk. So we will have another roughly half an hour to discuss informally with Damir related to his talk or any other